3, 2, 1. Alright, here we go, and welcome to the online section of Math 2070. So we're going to kick things off here by talking about the bread and butter of the class, the thing we're basically always going to go back to, and that is systems of linear equations. Now, it's not the full story of this course, but it's definitely the main tool we're going to be using. So we're going to jump right into it to start off with the main thing we're going to be working with. So let's start off with kind of a basic question. Just give us a bit of a flavor of how things are going to go. All right. So if I give you two lines, how many points of intersections can there be? So just in your mind palace, draw two lines. How many times can they overlap? Now, we're going to be Euclidean here. If you're not a Euclidean, the answer to this is a little more exciting. But in the world of Euclidean space, which is the usual 2- or 3-dimensional spaces we like to hang out in, basically there's only 3 possibilities. So if the lines are parallel, then there's no overlap, so there's no solution. If the lines are not parallel, okay, well then they can intersect at exactly 1 point. And now the infinitely many is the weirder one, because that means I just drew the same line twice, right? So I have one line on top of the other. Now, obviously, maybe you didn't think of that one in your head initially, but that is a possibility. You could have just drawn the same line twice. Silly as it may be, but that does mean there are infinitely many answers. All right. Now, visually, geometrically, you can convince yourself this is what happens. But how do we algebraically do this? All right, well, then we need an equation for a line, and when I say equation of a line, there's one of two things you might conjure up from your calculus days. Y equals mx plus b, or y minus y naught is m times x minus x naught. And respectively, this is the slope-intercept and the point-slope form of a line. However, there is a better equation for a line, one that you may or may not have encountered, but that is the ax plus by is equal to c. This is going to be our preferred format when it comes to linear equations. And note that this is actually a lot better because the y equals doesn't allow for vertical lines. Right, a line going through the point x equals -2, that vertical line there, right, it's not a function, so I can't have a y equals. But this new equation, ax plus by equals c, lets us get away with that. So it's a much better formula. Alright, so now that we have algebraically talked about what a linear equation is, so note for a normal line living in 2-dimensional space, we have an x and a y coordinate, but we can, of course, be in 3 dimensions, so you'd have an x, a y, and a z, and there's nothing stopping us from having as many dimensions as we want, so anything that looks like the variable scaled and added up equaling another constant, we'll call that a linear equation. And of course, once we run out of letters, we'll of our usual variety, we'll go over and steal some Greek and or Hebrew letters. All right, so that means then that now, if I wanted to talk about how would I solve the number of points of intersections of two lines, that means I have the following system of linear equations. I have an ax plus by is equal to an alpha, and a cx plus dy is equal to a beta. So this represents an equation of one line, and this represents an equation of another. So, hey, there we go, systems of linear equations. Like I said, I don't want to say everything we're going to do, but a lot of what we're going to do in this class will eventually boil down to how do I handle something that looks like this. And of course, we'll talk about the why you would want to handle something that looks like this and the various ins, outs, and what have yous about things that look like this. But you have, of course, probably ran into a few of these in your math life before this moment. So, for example, partial fractions, something like this usually pops up. But of course, there's other things that you may have encountered, and you may have already had a little experience with systems of linear equations and matrices before. Ooh, spoiling it. All right. So, as I've already said, basically, how these things work is what we are going to basically only do, but it's not a straight line, it's going to be serpentine. So, let's talk about actually solving these. And here we go. We've now replaced the A, the B, the alpha, the C, the D, and the beta with actual numbers. And here I'm using x1 and x2 instead of x and y. We'll vary between enumerating our variables, our unknowns we're trying to solve for, or versus just representing them as x, y, z, or something like that. Okay. Now, you can, of course, just brute force this, just work on the equation by itself, but as I've already let slip, what we're really going to do is use matrices to help us out here. Okay, so the unknowns, x1 and x2, are obviously what we're trying to solve, but if we really think about what this equation is saying, those unknowns, sure, are what we're interested in, but the coefficients and the right-hand side are really the determining factors. Right, the unknowns are always going to be these unknowns, but what determines how they behave is actually just the numbers, scaling them, and being added up, or being equal to them. So those are the things that actually matter. The variables actually don't. It's these coefficients and the right-hand side. So we can rewrite the system as this augmented matrix instead. So here I've taken these coefficients, put them there. So the -2 and the -7, and the -5 we put on the right-hand side. And here we use this bar to sort of represent what's on the right-hand side of the equals and what is the scalars multiplying the coefficients by the coefficients of the variables. Okay, so hence the name. The thing on the left is usually referred to as the coefficient matrix, and then the thing on the right-hand side, I've never really seen a good name for it other than the right-hand side. So. Now, what we can do to solve the system, so in other words, figure out how x1 and x2 are behaving, is perform what are known as elementary row operations. Now, these are the exact maneuvers you would be doing if you wanted to solve this system of equations right here without converting over to matrices. If I just gave you this and said, solve for x1 and x2, you would probably immediately start doing something like, well, I'll scale this by 2 and add it to that to delete this term. And the elementary row operations just give us a more algorithmic way of handling those sort of natural and innate math techniques. So, scaling a row by non-zero constant, obviously I can multiply both sides of this equation by 0, but that wouldn't do me any good. As an aside on that, one of my friends in college, a mechanical engineer, that was his go-to maneuver whenever he was working on a homework problem and he got stuck and he didn't know what to do, and so he just scaled both sides by 0 and said 0 is equal to 0, tell me I'm wrong. And which I will tell you are wrong, so. But that always reminds me of him whenever I talk about this. All right. Now, here is a technique, interchanging two rows, that is initially probably just aesthetic. You might go like, well, I want to work with this because this is a 1 rather than a -2. But as we'll see as we go forward, interchanging rows has some pretty interesting consequences, especially when it comes to the world of determinants. So we'll put a pin in that and revisit that. But that is a maneuver that is perfectly legal. And then the big one, replacement, which is when I go ahead and replace a row with a sum of itself with a multiple of another, which is what I already mentioned. This is the sort of the main row operation where we use this to eliminate variables. All right, so let's see all of these in action in our system. So here we go. So as I said, there's this aesthetic move of swapping rows. So I swapped row 1 with row 2 because 1 is better to work with than -2. Then I can scale this row by 2 and add it to that one, because then I get a 0, which is what I'm looking for. This row then conveniently gets scaled by 1/3, giving me that, and then I'll scale this row by -5 and add it to this one, giving me this. And now from here I can convert this back from an augmented matrix to a linear system by noting that row 1 is telling me that x1 is -8, and row 2 is telling me that x2 is 3. Good stuff. Hey, look at that. We have solved our first system of linear equations. We converted it over to a augmented matrix, and we performed our elementary row operations. And if you thought this was great, get ready, because we are going to literally do this every single day. Maybe not every single day, but we're going to do this a lot. We sometimes joke in the department here, this class is the applications of row operations course. So there's a lot of this stuff we're going to do. All right. And here we see it went very well. It went perfectly, even. And if we float back to our original question of, hey, how many points of intersection are there for two lines? Here we see I've got exactly 1 point. I have my x-coordinate, -8, and my y-coordinate, 3. Now, this went perfectly, and of course, sometimes things don't go the way we want them to. Okay. Before we get into that, let's note that some verbiage here. These matrices, we're going to call them row equivalent because I'm able to transform this one into that one using row operations. And the significance of this, again, will be reveal. The onion will pull back and reveal itself as we go forward. Okay. All right, so back to my previous point. So when we can find a solution, we'll say the system is consistent. But it's possible to have infinitely many answers. So something we've already addressed is we could have two lines that are exactly the same. And here we see that the equations are technically different, but if I take out my peepers and look at this one a little bit more closely, I see that line 2 is equation 1, just scaled by -2. So if I actually do perform my row operations, I'll actually get a big fat row of zeros at the bottom, because when I scale this by 2 and add it to this, hey. Now, of course, this doesn't tell us that there's no answer, it just tells me that I've got infinitely many choices, because really, I only had one line. Right, I just wrote it twice so that it overlapped, so there's infinitely many points of intersection. So that gives me this, and now if I wanted to talk about any solutions in particular, I can, of course, solve this for x2 in terms of x1. And sometimes we like to introduce a parameter here when we do this, because it just looks a little bit better. But here we see that x2 can be described as 1 half of 3 minus t. Beautiful. So here we see a case of being consistent, but having more than one answer. And it's possible, as we've already mentioned, that there are no solutions, two parallel lines. So, for example, if we modified the previous equation and had a -5 on the right-hand side in the second row, then if you tried performing some row operations, you'll get this. And if we convert this back over to a system, the second line gives us 0 is equal to 1, which is, I hope we all can agree, not true. Unless you're working, of course, in the integers mod 1, but in which case, I mean, you're full-on crazy person, so. All right. Now, so far we've only seen the case of two variables, right, and again that corresponds to two lines in usual two-dimensional space, but of course we can go over to three lines in three-dimensional space. And then you could take this and convert it over and then perform a bunch of row operations, and then you can determine consistency or how many solutions need to exist. So, our two favorite things in mathematics: do solutions exist? And if they do, are they as great as possible, meaning are they unique? Alright. I'll leave this one for you to go through and compute on your own, so feel free to, well, the video's over. At this point, we just hit the last slide. So right after this, feel free to go ahead and do your own little row operations on this and see what you find. Okay. There we go. We now know what a system of linear equations is, and we now have the basic technique of solving them, or at least the technique we're always going to fall back to, which is our converting over to an augmented matrix and performing our row operations. We got our new verbiage of consistent systems and inconsistent, and life is good. All right. So, next up, we'll talk a little bit more about what we could do with these row operations, what we could do with these matrices. So I'll see you in the next video.